continuation to our previous video, beta oxidation. So here I am showing you the beta oxidation schematic representation, diagrammatic presentation here. Here how a fatty acid is entering into the cell, and from there, how it is transporting to the mitochondria, and once it enters into the matrix of the mitochondria, how it is undergoing beta oxidation proper, and finally producing what are the substances and how they are producing energy. So this is fatty acid. Once it has entered into the cell, because of the enzyme fatty acyl-CoA synthase or thiokinase, it will be converted into fatty acyl-CoA. This is called activation of fatty acid. And once this fatty acid are activated with the help of carnitine shuttle, especially in case of long chain fatty acids, not the medium and short chain, because medium and short chain doesn't require carnitine shuttle, only long chain fatty acids. So these long chain fatty acids, with the help of carnitine, they will be entering by using enzymes CAT1 and CAT2. CAT1 present on cytoplasmic side, CAT2 present on the matrix side. Right. Once this fatty acyl-CoA enter inside the matrix, there are 4 steps. What are they? Dehydrogenation, and hydrolysis, again dehydrogenation, and cleavage. So these are the 4 steps for beta oxidation proper. In dehydrogenation, what is the reducing equivalence involved in first dehydrogenation step? That is FAD involved, and it converted to FADH2. Remember, note this point. And hydrolysis, you are adding water molecule. And dehydrogenation, you are using one more reducing equivalence, that is NAD, is converting into NADH2. So in cleavage, you are adding coenzyme A. You are adding coenzyme. So these are the 4 substances required for beta oxidation proper. So first step is by the enzyme acyl-CoA. Step 1, acyl-CoA dehydrogenase, where FAD is converting into FADH2, which is equal to 1.5 ATP. And the product is transinyl-CoA, and transinyl-CoA again undergoes not hydrolysis, hydratase. Here the thing is, you are adding water molecule here. So here this enol-CoA will be converted to beta hydroxy acyl-CoA, with the help of the enzyme enol-CoA hydratase, and this hydroxy acyl-CoA converted to beta keto acyl-CoA, by the enzyme beta hydroxy acyl-CoA dehydrogenase, where NAD is converted to NADH, and is equivalent to 2.5 ATPs. And this keto acyl-CoA, with the help of the enzyme thiolase, where coenzyme A involved, it converted 2 carbons into acetyl-CoA and rest of the part into acyl-CoA. And again this acyl-CoA will be continuously participating in the beta oxidation proper until it last 2 carbons will be liberated as acetyl-CoA. So this is the overview of beta oxidation proper. 4 steps you are supposed to remember. They are hydration, dehydrogenation, dehydrogenation, and cleavage. So these are the 4 main steps you are supposed to remember for beta oxidation proper. So summary of beta oxidation I'll give you example like palmitic acid. As I told you, 16 carbon 1, it undergoes 7 cycles, which gives rise to 8 molecule. As I said, last molecule again liberated as acetyl-CoA. So 7 cycles means last step 2 acetyl-CoA will be producing, so 8 acetyl-CoA. So beta oxidation of fatty acid, see the first step is FAD dependent and third step is NAD dependent. You see here 16 carbons, right? So this is 1 cycle, so 1 acetyl-CoA. This is second cycle, another acetyl-CoA. This is third cycle, another acetyl-CoA, fourth cycle, fifth cycle, sixth cycle, and seventh. At 7th, 1, 2, 3, 4, 5, 6, 7. At 7th cycle, one more extra acetyl-CoA is produced. That is, this is 7 plus 1 is equal to 8 acetyl-CoA. And all the produced acetyl-CoA will be entering into TCA cycle. And TCA cycle again it will undergo to form last product will be regenerated, that is oxaloacetate. Meanwhile, reducing equivalence will be produced, and they produce 10 ATPs as per the new calculation. So 8 acetyl-CoA into 10 ATPs giving rise to 80 ATPs. So summary, energetic point of view. So 7 FAD, 7 NAD, and 7 water molecule, and 7 coenzyme A will be utilized. So 8 acetyl-CoA into 10 ATPs, 80 ATPs into 1.5, into 2.5. So the net production, we will see the calculation here, coming slide. So 8 acetyl-CoA 80 ATP, 7 FAD 10.5 ATP, and 7 NADH 17.5 ATP. So gross total 108 ATP. But at the initial stage we have utilized 2 ATPs for activation of fatty acid. So you have to minus 2. So total 106. So 16 carbon palmitic acid is producing total of 106 ATPs. You see, whooping in number of ATPs produced by one molecule of fatty acid undergoing oxidation. Okay, so the efficiency of beta oxidation is about 33%. So coming to the regulation of beta oxidation, the availability of free fatty acid regulates the net utilization through beta oxidation. If we are in need of energy, tricyl glycerols undergo degradation, free fatty acid formation will be there. They will travel in the circulation, reaches to the wherever the cell, whatever the target tissue is required energy, there they undergo beta oxidation and provides the energy. The level of free fatty acid in turn controlled by glucagon-insulin ratio. So insulin inhibits beta oxidation, whereas glucagon promotes beta oxidation. So glucagon increases free fatty acids levels, whereas insulin opposing the effect by decreasing the free fatty acid levels, and it promotes, instead of breakdown, it promotes free fatty acid synthesis. CAT1 is a regulator of entry of fatty acids into mitochondria. Melanin-CoA inhibits CAT1 activity. Melanin-CoA will be getting malonate. Okay, will be forming from melanate, one of the intermediate of TC cycle. When you add CoA to S, melanin-CoA, and melanin-CoA inhibit the CAT1. So when there is a high formation of melanate, this will be converted to melanin-CoA and inhibits the entry of fatty acids into the mitochondria. Thus, during the de novo synthesis of fatty acid, beta oxidation is inhibited. So defects in beta oxidation, abnormalities in transport of fatty acids into mitochondria, and defects in oxidation can lead to deficient energy production by oxidation of long chain fatty acids. So we have already discussed carnitine shuttle importance in transportation of long chain fatty acids across the mitochondrial membrane and to the matrix, participating in the beta oxidation proper. If there is no availability of carnitine, or if there is any enzymatic defects like CAT1, CAT2, long chain fatty acids cannot cross the mitochondrial membrane and involve and participate in beta oxidation proper. So common features of the defects of beta oxidation is hypoketotic hypoglycemia, hyperammonemia, skeletal muscle weakness, and liver disorders. All these things related with this. Acyl-carnitine accumulates when transferase or translocase is deficient. Dietary supplementation of carnitine has been found to improve the symptoms in such cases. If the beta oxidation defect because of the carnitine deficiency, if you provide the carnitine external source, then it will be restoring the beta oxidation. So organic acidureas. What are organic acidureas? They are the disorders of metabolism of fatty acids, branched and aromatic amino acids, and citric acid cycles. They are all characterized by accumulation of organic acids in body tissues and their excretion in the urine especially. All these organic acids are excreted in the urine. It leads a condition organic aciduria. The patient present with acidosis, vomiting, convulsions and coma. The children often die in infancy. In case they survive, there is severe mental retardation and physical retardation because there is no energy left over at all. Because of the defect in the beta oxidation, because of this defect in beta oxidation, what happened? Carnitine, because of the carnitine will be storing as acyl-carnitine, and again the most of the acids of citric acid will be accumulating, and apart from that, what else here? Lysine or branched chain amino acids. So these are all will be accumulating, causing acidurias. Right. Diagnosis is confirmed by showing the presence of organic acid by chromatography. Dietary restriction, cofactor therapy, and substrate removal are general lines of management of treating organic acidurias. So here in the table I am showing few of the important organic acidurias, that is methylmalonic aciduria. So where the enzyme methylmalonyl-CoA mutates or B12 coenzyme, okay, to convert malonyl-CoA to methylmalonyl-CoA. Because of B12 deficiency, this methylmalonyl-CoA cannot be converted into malonyl-CoA, so there is no stoppage CAT1. So there will be keep on increasing of fatty acid oxidation, right? So in case of B12 deficiency, here the acceptor of methyl group by B12. So in case of B12 deficiency, there is no acceptor. So there will be keep on accumulation of methylmalonyl-CoA and it causes methylmalonic aciduria. And the clinical features are ketoacidosis, hypotonia, hypoglycemia, hyperammonemia and hyperuricemia, and propionic acidemia, and this is because of the odd chain fatty acid degradation. Propionyl-CoA carboxylase deficiency, propionic acid cannot be converted into acetyl-CoA, so it again leads to condition ketoacidosis, hypotonia, vomiting and lethargy. And medium chain acid dehydrogenase deficiency, where medium chain fatty acids cannot be degraded, okay, leads to condition acidosis, hyperammonemia, hyperglycemia and fatty liver. And LCA-DH long chain fatty acid dehydrogenase deficiency, okay, here the enzyme deficiency is long chain acyl-CoA dehydrogenase. non-ketotic hyperglycemia, low carnitine, increased acyl-carnitine levels will be seen in case of LCADH deficiency. And glutaric aciduria is because of butyryl-CoA dehydrogenase deficiency. Again, the symptoms are similar to the other acidurias like ketoacidosis, convulsions, progressive neurological defects, and cerebral palsy is one of the notable feature of glutaric aciduria. So that's all about beta oxidation overview and the regulation and organic acidurias of beta oxidation of fatty acids. Thanks for watching. Thank you.